Thank you for the invitation. My name is Jorge-Luis Barrera. I'm a staff researcher here at Livermore National Laboratory. And today I'm going to present a portion of one of our next generation institutional codes that does design optimization, in particular shape and topology optimization tools that have some abstractions that are based on MFEM. So when I say, okay. So the code that we use, the software is the LiDO code, the Livermore Design Optimization code. And what this software does is it allows the user to use a suite of optimization tools, ranging from, well, gradient-based tools like nonlinear programming techniques, think MMA, IP-opt, to the other extreme of gradient-free optimization, think what you can see in the libraries like PyTorch. And we use these tools to solve several design optimization problems that can be the traditional ones, like the structural optimization, like maximizing the stiffness of a structure or minimizing the mass while keeping the stresses under a particular threshold. And we do this, we can also work with other physics, think or more complex applications like in additive manufacturing processes, where you may need multi-physics, transient and nonlinear phenomena to represent this phenomena. So overall, LiDO can do quite a number of things, but in this talk, I'm going to focus on gradient-based shape and topology optimization. And before I go into the details, I want to acknowledge that I'm the one talking, but most of the people that have worked pretty hard on this code are here on the right as part of the LiDO team. And I'm also showing the Serac team. I'm going to explain why in the next slide. But you might be familiar with what this code does if you were here in this workshop last year. Jamie Branwell gave a very nice presentation about Serac. And before I start LiDO is not open source, but we're open to collaborations. We have some external collaborators. So if you're interested, if anything that you see here today resonates with what you're doing, then we are open to discuss and probably give you access to the code. Now, when I say LiDO, think LiDO, what it does is it owns the design components. What optimization solver you use, what parameterization, how you parameterize your problem, what the design variables mean, and also what kind of interest, what metrics you use to assess where you have an optimal value of and how you construct your optimization problem formulation. But to get this quantity of interest, you have to analyze your engineering application of interest, right? And Serac is one way of doing that. In this case, I'm saying that Serac owns the physics. So here you solve your linear elastic, nonlinear mechanics, any physics that you care about. Here, if you have a structural problem, this is where you get your displacement from, right? And both LiDO and Serac are based on MFEM, meaning that the meshes, the finite element spaces, and for LiDO and shape optimization in particular, as I will explain later, the morphing capability of the mesh is also done thanks to the functionalities that are already in MFEM. Now, the thing is that I said that Serac could be used, and that is because the way LiDO has been implemented is such that you can't exchange modules. And as long as you provide the information that is needed for a particular module, then you can use your own implementation, because we have what we call the graph implementation. And to explain that, I have this example of a graph. So for a typical optimization problem, the benchmark compliance minimization with mass constraint. The starting point is the decision variables, right? And then we construct the graph here using LiDO, defining each one of these nodes and how they are connected with each other. And then we define also the objective and constraints, in this case, compliance, and the constraint here is the mass. So to solve the optimization problem, well, first we operate forward. We perform the forward physical analysis to compute our performance metrics to know what we want to optimize, what we care about. And then since here we do gradient-based design optimization, we need to compute the gradients. And to do that, we go backwards, meaning that we go from the objective and constraints all the way up to the decision variables. And in this graph implementation, we use like a chain rule idea. So when you move forward, you provide whatever is needed for that operator to perform the operation that it has to perform. So for example, if you need a mass, if you want to compute the mass, you may want to provide the density, right? And the mass is already aware of the mesh, so you can get the scalar back. And going backwards in the sensitivity analysis, you have the chain rule. So you just perform the component of that chain rule corresponding to that operator. And this is pretty powerful because think, for example, you're not using Serac or you're using MFEM directly, or another open source code, even if it's Phoenix, DL2, whichever software you have. You already have a model, something for your physics, but you still want to take advantage of what we can provide in LiDO. Then what you can do is that you can exchange whatever is happening in this node. And as long as you just need, in this case, material properties and can output displacements, and going backwards, you can still provide derivative with respect to this material properties and densities, then you should be able to do that seamlessly in LiDO. Now, but what can we do in terms of systematic design optimization? We have mainly two classes of approaches. The first one is topology, and the second one shape optimization. And there's more of one way to define this. So when I say topology optimization, I mean density-based, volume fraction-based topology optimization, meaning that I have a continuous fictitious density field on a fixed domain that evolves throughout the optimization process. And with shape optimization, I mean clearly defined boundaries of your problem, and I have shape sensitivities that drive the design. So probably more visually here. Here on the left, you have more like pixels that change color, and on the right, you have clearly defined geometry that evolves in the optimization process. So on the left in topology optimization, you have a field that parameterizes something like material properties. And on the right, you have, again, you parameterize the geometry itself. Now, you might have seen some commercial software that mostly does topology optimization, and that's because shape optimization can be complicated for a few reasons. I'll explain more on this, more about this later. But before, let me show you a couple of topology optimization results and how the graph works. So first, I have this mass-more part design. So think this is a two material problem in which you have blue and gray material, the two materials. And let's say you want to get the material distribution of both materials such that you get to a target mass, center of mass, and multiple momenta of inertia, which are described here. So I think it's just, you want to get to specified values. And since you have a continuous density here, fictitious density, then I want to avoid having intermediate densities such that, and then this P, which is the parameter of the density, I'm penalizing intermediate densities as the objective. If I look at the graph, it looks pretty involved, but one thing that I want to highlight here is that in LiDO, we have this abstraction, we call it the expression parser, that if we define these basic components in a basic graph, like the mass, the moment of inertia, combining them, providing this simple algebraic expressions can be done automatically by the LiDO graph, meaning that I can just write this out as a text string, and then the graph that you see here, at least this operations, the multiplications, division, subtraction, etc., will be done automatically in the graph in LiDO. And of course, the derivatives too. And for completion, yes, like this is how the optimal design for this problem looks like. Now, let's add some physics and go still in 3D. This is field-based octet truss lattice structural design. There's some story behind this, but just due to time constraints, I want to highlight that in this case, we have a mesh that is generated outside MFEM, in this case, qubits. So you have an Exodus 2 mesh, and you have two different blocks, node sets, site sets associated with those blocks. And we, thanks to MFEM capability of reading this type of Exodus 2 meshes, these blocks are interpreted as element attributes, and the boundary attributes are just the site sets. And in this case, we want to optimize the volume 1 region while keeping the skin, the volume 2, fixed. And you have a fictitious density that represents the truss, the lattice structure in that domain. So once again, I'm just highlighting the flexibility of using MFEM in our LiDO framework. Now, we can do more than topology optimization. In this case, for example, we also wanted to, we could have the freedom of changing the external shape while keeping the thickness of the skin constant. So we did also some shape optimization separate from topology optimization. Another nice thing about the graph implementation is that once you have these two components, you can also combine them and do, in this case, shape and topology optimization together. Now, in terms of shape optimization, the rest of my talk is going to be about this. I am leading a project about this, and this is ongoing work. So when I talk about shape optimization, at least the way that we do it here, is that it has a few components. So when you want to shape optimization, you have to parameterize explicitly your shape, right? or implicitly, but somehow you have to have a description of your shape. So you can do that in more than one way. For example, you can combine simple primitive like spheres, cubes, and cylinders to generate more complex one. But of course, you have a very restricted design space here. A different form of doing that is the so-called free-form shape optimization, in which you can perform like drastic changes in your shape in search for an optimal. So the geometry model is something that you have to take into consideration as part of your optimization framework when you solve a shape optimization problem. In terms of meshing here, we leverage MFEM's team-ups functionalities. I'll talk more about this in the next slide. And in terms of the gradients, of course, if you do gradient-based optimization, there are some equations associated with it. Since we're at lunchtime, I'm not going to spend too much time showing more equations. I think you have seen enough. But yes, keep in mind that whatever I'm going to show in the next few slides, there's of course some effort into making the formulations robust enough to be able to get good optimal solutions. And since this is ongoing, something that we're interested in is in doing the shape control, which can be seen as a few things. One of them is achieving provided minimum feature size, minimum length scale in the optimal design, such that they're actually manufacturable and they're actually useful for the user. And again, when I say we, what we're doing here is not me, it's my team. So this is work done by primarily Keaton on the meshing side, Matthias and Kenny on the shape optimization techniques that I'm going to show in a couple slides, and our advisors. Now, before we get into a shape optimization problem, the way we do this, so we first have to do some pre-processing of our shape optimization problem. And we use TeamUp for this. I'm not going to talk too much about what is behind this, just briefly to remind you, TeamUp has like this function that you minimize that has two components. The first one is the mesh quality metric, and the second one is the actual fitting of the mesh to whatever shape that you want to give. And in this case, sigma is this distance field, the level set field that you use to as a reference the ISO contour to get the fitting. Now, the way we do this is that we have an initial unstructured mesh, and then we morph the initial mesh such that we have an initial point in our optimization problem. You can see here examples in 2D and 3D. And we do this not only at the beginning, but also throughout the optimization problem, right? In this version of shape optimization that we're doing, we have conformal meshes. So we morph the analysis mesh where we're performing the finite element analysis from beginning to end in the optimization process. But even if you're not interested in shape optimization, you can still leverage TeamUp to avoid doing remeshing. And just to show you something, a simple example, you have two concentric cylinders, in which here I'm showing just the inner shell, in which you can parameterize whatever type of geometry that you want to provide. In this case, let's say you want dimples with different arrangements and depth, and you don't want to be remeshing this every time you want to test something different. So you can start with a very simple mesh, and using TeamUp pretty much just morph the mesh to whatever type of analysis geometry that you need for your problem. So now you have the initial mesh. How will we perform shape optimization? There are two options. I'm going to present two options today. We have tested variations of this, but overall, the option one is the way called node-aware shape optimization. And here, the design variables of the optimization problem explicitly are defined as explicitly the displacement of the coordinates, the locations of this node of your mesh, as you can see here in black and red. And the option two is one in which you have a higher dimensional level set function from which the zero ISO contour is used to provide the interfacing or the external boundary of our problem. In option one, we have just one mesh. We use two, but we use one mesh. In option two, we have, for describing the level set field, one fixed background mesh that doesn't change, and an analysis mesh that we morph throughout the optimization problem to get our results. Now, to show first option one, here's this stress optimization problem in 2D. This is a benchmark problem. I think you have shear loads here for the analysis, and also we have rollers for the design, and we only want to see what is the optimal shape of this hole such that we minimize the stress of the configuration. And you can see the initial configuration here and the optimal with edge refinement. This has an analytical solution. This is just to verify that everything works according to the theory, and also to showcase that thanks to MFEM, we can do very easily H and P refinement just with 1 or 2 lines of code. We can further discretize this much better. But also, this is not, so far I've presented geometric and structural problems. We can also work with other physics, because again, in LiDO, you just exchange some of the components. And if you just want different physics, you can just use a different code, or you have your implementation, or just solve a different optimization problem. And in this case, I'm showing a thermal management application in which then you want to maximize the energy generated by the system while preventing the temperature of the system to go above a threshold. And what you can control in this case, without going too much into details as a time constraint, is the shape of this of the cooling fin that you see here in blue. So you can see how the optimization gets to a different shape, and how the temperature distribution is much better in terms of energy produced by the system. And also, thanks to some of MFEM features, you can see that here we can have some small thin features. We can have some indirect control on how small this gets by providing some explicit control on regions of our design domain, and restrict how much the shape can vary in those regions. We're still testing different alternatives, but this is one way of doing it. And in 3D, going back to structural, here you have a dam problem, and we test both compliance and stress. And you can see in the simulation how option 1, in which like you have the optimization variables explicitly changing the coordinates of the mesh, can help us, can get us to optimal designs with large shape changes, as you can see here in both examples. There's more to this. We're preparing journal papers, and once they're ready, if you're interested, I'll be happy to share those with you. And finally, we have option 2, which was a level set based shape optimization. We got these results pretty recent, so bear with me. Remember, I told you that there are 2 meshes in this approach. The first one that you see on the top doesn't change, and this has the level set field, and the one at the bottom is where the analysis is performed. And here you will see that team-up is going to change the mesh as it evolves, but also what we're doing is that we are changing the element attribute such that the morphing is not extreme. So you can see here how we're changing the element attribute, and you see that despite like there are topological changes everywhere throughout the optimization process, in the end, the mesh, we use the same mesh throughout the optimization process, and we just have small morphing throughout it. And an important component here, and again, this is ongoing, is that in shape optimization, level set base, we want to have a smooth, regularized level set field. And in this case, we're achieving that by having our design level set field mimic a distance function. And we do this by using one of MFEM's mini apps, the distance one. And you can see here how this level set field throughout the optimization problem is well regularized. So this is a benchmark problem, but this is very nice for more complex applications. This helps the methods be more robust overall in shape optimization with level sets. And in summary, so I mentioned LiDO can work with Serac, and both LiDO and Serac are based on MFEM. We use the graph paradigm, which help us just exchange certain components, and we can use your implementation if you are interested in using what we can provide with LiDO. And we can just by exchanging these building blocks. And I show you some topology optimization and shape optimization results with 2 different approaches. And that's it. Thank you very much for your time. I know I think I'm on time. So if you have any questions.
Does anyone have any questions?
I have one. Any plan for unstructured mesh adaptation in your level set framework?
Can I plan for a unstructured mesh
adaptation?
Can I plan for?
Any plan for unstructured mesh adaptation? Like you are using a fixed mesh
Yeah.
right now. For level set method, you usually want to do body fitted mesh adaptation. And so is it something that is in the pipeline or?
That's so we're using team up. So whatever that we're not just using team up. Part of the project consists of exploring how much we can do with team up and further develop it such that it's amenable for shape optimization. Depending on what type of problems we want to solve, we may go in either or one direction. But overall, I would say that we are going to continue looking into team up to make it more robust for shape optimization in 3D. So far, I think off the top of my head, most of the problems that I'm interested in would be with structure meshes, but that can change tomorrow.